All right, so our next lesson on limits is about the squeeze theorem. So this is a very special theorem that works in very specific scenarios. A couple years ago, it was on the AP exam on the free response part, and a lot of teachers freaked out about it because they hadn't been teaching the squeeze theorem because it had not ever been on the exam. But it's always been a part of our curriculum, and it showed up one year. So it's something you need to know how to do. And it's pretty easy because it's going to be set up the way that it needs to be set up for you to use the squeeze theorem. So you should automatically recognize it because you're going to have basically this statement right here. All right, if h of x is less than or equal to f of x is less than or equal to g of x for all of x in an open interval containing c, except for possibly at c itself, and if the limit of h of x is equal to L and the limit of g of x is equal to L, then by the squeeze theorem, the limit of f of x has to equal to L. All right, so let's show you an example of what this looks like, and then we'll talk about how this all works. All right, so we have if 2 is less than or equal to f of x is less than or equal to x squared plus 2. For all x, find the limit as x approaches 0 of f of x. So what they're doing here is they're asking us the limit of a function they didn't tell us anything about. We don't know what f of x is. We don't know its equation. We don't know what its graph looks like. We don't know anything about f. Okay, but we can solve this problem. And the way we can solve this problem is by using the squeeze theorem. Okay, so 2 right here, even though it's a single number, that counts as a function. H of x, x squared plus 2, that's our g of x. And then we have our f of x in the middle. Okay, so sketch a graph to illustrate. So I'm going to sketch h of x, which is just a horizontal line at y equals 2. Okay, that's my h of x. All right, and then g of x is the quadratic parent function shifted up 2 units, so that's going to be right there. So something like that. All right, and then all I know about f of x is that it's between these two functions for all x's. So that means it's somewhere in this part, like that. Okay, so I'm just going to draw a random function here. Let me label. This is g of x. All right, so I'm just going to draw a kind of random function like that, and that's going to be our f of x. All right, now notice what our limit is. We want to find the limit as x approaches 0. Okay, well, that's this point right here. And this is the important thing. The squeeze theorem means this function is going to be squeezed down into one point. So you see how g of x and h of x both intersect here at 0, 2? Well, that means f of x. Since it's in between these two, f of x has to squeeze down to that same exact point. All right, so here's how we show our work over here. So they gave us the inequality in function notation. So now we're going to make them all limits. So we're going to do the limit as x approaches 0 of 2 is less than or equal to the limit as x approaches 0 of f of x, which is less than or equal to the limit as x approaches 0 of x squared plus 2. Okay, so the key here is that 2 of these limits you have to be able to solve. So we can solve this one because that's equal to 2. Limit of a constant is equal to the constant. We cannot solve the middle one, and that's good. We didn't want to be able to yet. And then the right one, if we do direct substitution, plug in 0, we get 2. All right, and that's it. So 2 is less than or equal to this, which is less than or equal to 2. The only possible answer is 2. They're all equal to each other. So that means the limit as x approaches 0 of f of x equals 2 by the squeeze theorem. All right, that's it. So let's do one more example. All right, graph the function and the equations in the same viewing window on your calculators. Let me get that booting up. Then use the squeeze theorem to find the limit as x approaches 0 of f of x. So this time they did tell us what f of x was. So I just want to show you what happens. So x sine of 1 over x. All right, so if we tried to solve this one, we would end up with 0 multiplied by sine of 1 over 0. All right, and this isn't good notation, so that's why I didn't write an equal sign here. But basically, 1 over 0 is infinity. Think about the number on the bottom gets really, really small. So the fraction gets really, really big. All right, and so all that means, though, is that sine is just going to keep oscillating over and over and over again. Okay, it's not going to approach infinity or anything like that. So this doesn't exist. Well, this is in an indeterminate form, is what I should say. And so we have to find the value that way. We can't solve it just by direct substitution, and there's no algebra that we can do with this to like simplify it. Okay, so that's why the squeeze theorem is what we're going to use here. Okay, so I'm going to go to my calculator, and we're going to graph our two absolute value functions, and then we will graph the f of x in there as well. All right, so you can get your absolute value by hitting this template button and going right there. So absolute value of x in f1, and then negative absolute value of x in f2. Okay, so it's looking like if we're approaching 0, hopefully our graph will pass through that point right there. And so f3 is going to be x, and then you have to be careful in the inspires. If you just do sine right afterwards, here, let me get it from the trig menu. So trig, sine. See how it's italics like that? Italics means the calculator does not recognize what you typed in. Okay, it should go to regular print. Okay, and the reason is because it's thinking that x sine is a function that called x sine, and it's not recognizing that it's x multiplied by sine. So you actually have to type your own multiply symbol in there, and see how the sine went to regular print. Now the calculator recognizes this. All right, so 1 over x in there. All right, it really doesn't look too bad. You can see how this function does look to be in between those two. So I'm going to show you, though, that if we zoom in here, there's something crazy happening. So menu, Windows zoom, zoom in. I'm just going to zoom in right here on 0, 0. All right, y'all can kind of see it starting now. There's all the oscillating. So as we get closer and closer to 0, it's oscillating faster and faster and faster and faster and faster and more and more and more and more. All right, but you can see that all those oscillations top out where y equals absolute value of x and bottoms out at y equals negative absolute value of x. All right, now that I'm this far zoomed in, the calculator has lost some precision. So you can see how it's not showing us it going all the way up and all the way down each time, but that is what's happening there. But nevertheless, it's always in between these two functions. And so that means that the squeeze theorem is going to apply here. Okay, so let's go back to our notes and let's write out our problem. So I'm going to just put a question mark there. All right, so the function on the bottom, let's draw it out here. So we have this y equals negative absolute value of x. And then we have this y equals absolute value of x. And then we have and it eventually just kind of does that. But it's not a sharp turn like that, so draw that more curved. All right, anyway, this is our point of interest over here. Okay, so let's set up our inequality. So negative absolute value of x is less than or equal to x sine of 1 over x, which is less than or equal to the absolute value of x. And actually, I'm not going to write this out every time. That's annoying. They gave us a name. This is called f of x, so I'm just going to put f of x. Our problem was stated this way. Limit as x approaches 0 of f of x, so I'm just going to keep the f of x there. All right, so now I have the limit as x approaches 0 of the negative absolute value of x less than or equal to the limit as x approaches 0 of f of x, which is less than or equal to the limit as x approaches 0 of the absolute value of x. Okay, so this limit we should be able to solve. Direct substitution, that is equal to 0. This limit we can't solve, as we showed up here. And then this limit, direct substitution, is equal to 0. So the limit as x approaches 0 of f of x is equal to 0 by the squeeze theorem. Okay, you never have to invoke the name of a theorem on the AP exam if you're using it. You just have to make sure you have all the parts that are necessary. So having this inequality of the functions, then having the limits of each one in there, and then your conclusion would be what you need. But I'm going to invoke the name of the theorem. We're going to learn some other theorems this year, and we're going to do the same thing with those. Again, we want to write our answers so perfectly that they don't have a choice but to give us the point. So this is kind of going to that. Yeah, even though it's not required, it's still good practice. All right, quick and easy on that one. So hope you all enjoyed, and I'll see you on the next one.